created by Mindsticks Foundation Trust.
Welcome, students, to our explainer for today. We are going to trace the fascinating journey from raw earth to pure metal. We'll be moving through 5 key stages: the nature of ionic compounds, the basics of metallurgy, separation by gravitation, magnetic and flotation methods, and finally, extracting pure aluminum. Let's dive right in.
Section 1. Nature of ionic compounds.
Before we get into how to actually extract metals, we really need to understand the incredible strength of atoms when they bond tightly together. We call these ionic compounds. If you look at the data, you'll see it takes massive amounts of heat energy to melt or boil salts like magnesium oxide. It melts at a staggering 2,852 degrees Celsius. That is incredibly hot. This just goes to show you exactly how strong the attractive forces between these positively and negatively charged ions truly are. In their natural state, they are very hard, brittle solids.
But here is the really interesting part. While they're hard solids initially, consider what happens when we dissolve them in water. The water molecules step in, orient themselves in a very specific way, and actually overcome that original intermolecular attraction, separating the ions. Now, these separated, mobile ions allow the aqueous solution to conduct electricity beautifully, which we can demonstrate with a simple electric cell and graphite rods. Because they conduct electricity so well, we call them electrolytes.
Section 2. The basics of metallurgy.
So let's zoom out a bit. Let's shift our focus from a beaker in the laboratory to the Earth itself. The grand question is, how do we extract these locked-up metals from nature so we can actually use them in our daily lives? Well, it all comes down to understanding what we're mining. The entire science of metallurgy revolves around one fundamental battle. We have to separate the valuable, profitable metal-bearing minerals, which we call ore, from all the worthless, rocky impurities, like soil and sand, which we call gangue. It's basically a rigorous, large-scale purification process.
Which brings us to Section 3, separation by gravitation.
The most foundational way to separate the heavy ore from the light gangue is by simply using the law of gravity. Take a clever piece of engineering like the Wilfley table. We pour powdered ore onto a continuously vibrating inclined surface. As a steady stream of water flows over it, the lighter dirt, or gangue, just washes right away. Meanwhile, the heavy, valuable, concentrated ore gets safely caught behind narrow wooden slits, known as riffles. It's an incredibly simple but highly effective use of gravitational sorting.
Building on that exact same idea, we have the hydraulic separation method. This utilizes a tapering tank. We introduce a really forceful jet of water from the lower side. This upward force pushes all the light, worthless gangue out through the upper outlet. But the heavier, pure ore particles, they aren't lifted up by the water. Instead, they collect safely down at the bottom. Once again, we're letting gravity do all the heavy lifting for us.
Section 4. Magnetic and flotation methods. Sometimes, students, gravity just isn't enough. When the particles are of a similar size or weight, we have to rely on physics and chemistry to do our sorting. Take ores containing magnetic ingredients, like iron, or non-magnetic ones like cassiterite, which is a tin ore. Here, we use an electromagnetic machine. We pour the powdered ore onto a conveyor belt that's moving over an electromagnetic roller. The magnetic parts stick to the roller and are carried a bit further to fall into one specific collector vessel, while the non-magnetic dirt just falls straight down into another. It's a really elegant industrial application of magnetism.
Now for our next method, I want you to picture a colocasia leaf. You know how water beads up and rolls right off it without getting the leaf wet? That water-repelling property is called being hydrophobic, and it's exactly how we isolate certain metal sulfides. We can contrast this with hydrophilic substances, like common salt, which absolutely love water and get wetted by it easily.
We take full advantage of these properties in the froth flotation method. We mix finely ground sulfide ore with vegetable oils, like pine or eucalyptus oil. Then we blow compressed air through the water to create lots of bubbles. Because our metal particles are hydrophobic, they prefer the oil. They get wetted by it and float up to the surface in a thick, foamy froth. The water-loving gangue particles, on the other hand, get wetted by the water and simply sink down to the bottom. And a central agitator keeps the whole mixture moving perfectly.
And finally, Section 5, extracting pure aluminum.
For our final step in this explainer, let's look at aluminum. This is a metal so highly reactive that it needs a very specific and advanced chemical extraction process. You see, it has an atomic number of 13 and a valency of 3 in its outermost shell. Because it's so reactive, you will never find it sitting all by itself in nature in a free state. Even though it's the third most abundant element in the Earth's crust,
It is always trapped in an ore called bauxite, mixed up with tough impurities like silica, titanium oxide, and iron oxide.
To concentrate this bauxite and strip away those stubborn impurities, we use a brilliant chemical trick called leaching. Leaching is the crucial first step where we soak the ore in a specific chemical solution for quite a long time. The genius part here is that the solution reacts with and dissolves only the desired metal. The unreactive gong is just left behind, meaning we can easily filter it right out.
Let's look at the famous Bayer's process. First, we grind the ore in a ball mill. Then, we heat this powdered bauxite with a concentrated solution of caustic soda, that's sodium hydroxide, at 140 to 150 degrees Celsius under really high pressure in a digester. Because aluminum oxide is amphoteric, it reacts to form a water-soluble liquid called sodium aluminate. The solid iron oxide impurities, they don't dissolve at all, so we simply filter them out of the solution. Alternatively, there's Hall's method. This relies on aqueous sodium carbonate to achieve the exact same result. It is heated in a digester to create that same water-soluble sodium aluminate, allowing us to filter out the solid impurities. The fundamental chemistry lesson here is exactly the same. We're using complex reactions to turn the metal into a liquid state, separate out the solid dirt, and then eventually precipitate the pure metal back out for our use.
Students, I really want you to think deeply about the incredible journey we've covered today. Think about it. From raw, muddy earth pulled from a mine, all the way to the shiny, pure metals that build our airplanes, our buildings, and the modern machines we use every single day. How will mastering these hidden chemical forces and precise extraction processes continue to shape our technological future? The earth provides the raw materials, but it is science and metallurgy that unlock their true potential. Thank you for joining me on this explainer. Keep studying and keep wondering.